going to talk about series and some of the tools that we used in the workshop last term to analyze series. So I'm going to start by talking about Zeno. So Zeno was a Greek philosopher, mathematician, who was born in about 495 BC, and he is well known for his paradoxes. So he has multiple Zeno's paradoxes, and we are going to talk about one of them because it is a great motivator for series. So this paradox goes like this. You have an archer, you have a target, and in order to hit the target, the archer's arrow has to travel half the distance, half of the remaining distance, half of the remaining distance, and over, always traveling half of the remaining distance in order to hit the target. So the paradox is this: does the arrow ever hit the target? There are some arguments that we can make about that. So the first thing we can do is we can think about just naturally, if I shoot an arrow at the target and we kind of ignore the other variables like wind and things that could knock it off course, if the arrow is aimed well and it's going to hit the target, then it's going to hit the target. So just thinking naturally about this process, if I shoot an arrow at a target, barring some kind of crazy scenarios, my arrow should just hit the target. That's how it's going to work. However, if I'm traveling half the distance and half and half and half, there's always going to be another half of the distance that I can go before I hit the target. So that means there's always a little bit of space and I never hit the target. So that's where this paradox comes in. Because it's true, the arrow does have to travel half the distance and half of the remaining distance. But if it's continuing to do this, will it ever hit the target? Or will there always be some sort of little half space that we can still travel? The good news is, just thinking logically about, if I shoot an arrow at the target, it should hit the target. There's not going to be a point where it just stops slightly far away from our target. Eventually, it's going to hit the target. So that's a good indication that the answer to this question of traveling half the distance over and over, will the arrow hit the target? It's a good indication that even in that situation where it seems like it won't, it's still going to hit the target. And so we're going to analyze this mathematically. So the first thing that we're going to do is we're going to attach some numbers to the situation. So what I'm going to do is I'm going to tell you what the distance between our archer and our target is. So this distance is going to be 1. We could name it whatever we want. We could use a variable like the letter D for distance. We could use a different number. But it doesn't matter because in the end, it's just a multiple of our distance, right? So if I have 1 and I wanted my distance to be 250 feet, I would just multiply everything I'm about to do by 250. So it's okay to just go ahead and call this 1, and that's what we're going to work with it. It's generalizable still, even if we just have that number 1. So if the full distance is 1, then the first distance that my arrow travels is 1/2. So it travels half of the way to 1. Now, the next little distance we're going to travel is going to be half of the remaining space. So 1/2 of 1/2 is 1/4. And our next gap that we're going to travel is half of that remaining quarter. So it's going to be 1/8, and so on, 1/16. And as we get half and half and half, it's going to be a 32nd, a 64th, etc. So now we have some numbers, attached to this situation. So what can we do with these numbers? Well, the first thing I want to do is actually sum up my distances. I want to say, okay, so how far has the arrow traveled? And remember, my goal is to say that the arrow is going to hit the target, which means my goal is to say that it is going to travel a total distance of 1. So right now, if I wanted to figure out how far the arrow has traveled in its first leap, it would be 1/2. If I wanted to see how far it had traveled in its first 2 leaps, then it's going to be 1/2 plus 1/4. And so basically, if I want to figure out the total distance that my arrow has traveled, I just need to add up all of these little distances that it travels through each jump. So I have 1/4, and then an 1/8 I also need to add in there, a 1/16, and this goes on forever. So, vocab time, I used the word series earlier. And this that I have written out right here is a series, specifically an infinite series, because there are finite series. But usually when we use the term series, we by default assume it's infinite. If it's a finite series, we say it's a finite series. So the only difference between those two things is where we stop. Whoa, that's not what I wanted. Is where we stop. So if I only have this much of it, that's a finite series or a partial sum. If I have the whole ... it's an infinite series or just generally series. So vocab there. So we have a series here, and we're going to talk about 4 ways to look at this series. And we've actually already done one of those 4 ways. So one of those 4 ways is to use a visual or logical reasoning to conclusion about what's happening in this series. So I talked about the arrow is going to hit the target, which means I am predicting it's going to travel this full distance of 1. Another way we can do visuals, I use bar models a lot. I'm a big fan of them. So if I were to visualize this with a bar model, I would say, okay, we've got a 1/2 here, and then we travel 1/2 the remaining space, and 1/2 again, and 1/2 again. I need my normal pen. So if the whole thing is 1, and I travel 1/2, and then a 1/4, and then an 1/8, then a 1/16, if I keep going, looking at what's happening is I'm filling up this bar, so I'm expecting my series is going to go to 1. So that tends to be people's kind of least favorite method here, is making this visual. But it is really important because this lets us get some logical reasoning about what's happening with something infinite. You have to reason about what's going on before you just start applying mathematical rules. And I'll explain a little bit more why that is in a bit. So, our first method for analyzing series is logic and visuals. Our second method is called the sequence of partial sums. So, breaking down, what is the sequence of partial sums? It is pretty much exactly what the name states. It's a sequence. A sequence is a list of numbers, and it's a sequence of partial sums. So what we're going to do is we're going to add up parts of our series and just list them out, a long list of numbers. So if I add up just one term in my series, I get just 1/2. And if I add up 1/2 plus 1/4, I'm going to get 3/4. If I add up 1/2 plus 1/4 plus 1/8, I'm going to get 7/8. And then I'm going to get 15/16. Do you see a pattern happening here? So our next one is going to be 31/32. And so on. It's going to continue going on forever, just like the series does. So an important thing about the sequence of partial sums, the sequence of partial sums is a sequence. So it's separated by commas. It's a list of numbers. It is not itself a sum. Do not write the sequence of partial sums like this. That is not the sequence of partial sums. That's just a brand new series. And that doesn't tell us anything about this series. Our sequence of partial sums does tell us about this series. So just from the sequence of partial sums itself, I can start looking at what's happening to my numbers. Sometimes it's nice to put them in decimals. If you don't see anything coming from the fraction, if that's not clear, you can totally represent it as decimals, and that might make it a little bit more obvious. But from here, I see something happening already just in how far it is. So of course I see a pattern between these numbers, but specifically when I'm looking here to see what is my series approaching, I want to look at what does it look like our numbers are getting closer and closer to. And each of these fractions are getting closer and closer to 1. So if I continue going, and so I have 63/64, that's going to be even closer to 1 than my previous fraction. So again, this isn't super precise. Just like logic and visuals, this is just kind of looking at what's going on and seeing if it looks like it's approaching something. Now, our last two methods are going to be our more formal methods. So our third method is probably what I think is most challenging. So it uses our sequence of partial sums, and we're going to find an equation for the nth term. And then we're going to let n go to infinity. So I'm going to talk about what I mean by that. So here I'm going to give myself some space. So what I'm going to do is I'm just going to add more to the canvas size because I don't want to lose what I already have. Okay. So if we think of the sequence of partial sums and we say, okay, this is the first thing in the sequence. This one's our second, our third, our fourth term, fifth term, sixth, etc. I want to be able to tell what is my nth term. So instead of having to always go from the previous one to the next to figure it out, I want to be able to just jump anywhere in this series by plugging in a number for n. So that's my goal here. So there are a couple ways we can go about this. I'm going to show you how I see these patterns, but there's a lot of ways you can see it. And it's not always going to be the same for every series. So that's why I say this is one of the trickier things, because you have to be able to translate from a recursive pattern. So recursive means going from one term to the next. So you always need to know the previous term in order to find the next one. To an, so that's recursive. To an explicit pattern, which is a function. And so that's what we're looking for. We want to be able to take any n and immediately know what fraction it is without knowing what the previous one is. So I notice a recursive pattern. Ooh. And that recursive pattern is that every time I go from one to the next, my denominator is doubling. So when I see any sort of multiplication happening every single time and just multiplication, I know I'm going to have something exponential. So that's called a geometric sequence when you have that multiplication over and over. And that translates to an exponential explicit function. So the recursive pattern for the denominators is geometric. So that means the explicit is going to be exponential. So thankfully, this one is pretty straightforward. So if I have 2, so I'm just going to write down my denominators. 2, 4, 8, 16, 32, 64. So 2 is one copy of the number 2. Sorry, I'm just trying to clean up the space a little bit. So our first term has 1, 2 on the denominator. Our second term is 2 times 2. And this one is 2 times 2 times 2. And so on. So the number of 2's that I have matches the term number, or n. So I can rewrite my repeated multiplication using exponential. So this would be 2 to the first, this would be 2 squared, this would be 2 cubed, 2 to the fourth. And every time this number always matches my term number, which is generally described as n. So that's how I'm going to get my equation here. This is, on the denominator, 2 to the nth power every time. So when I'm at the third term, plug in 3 for n, 2 cubed gets me 8. Now, the numerator is a little bit more tricky, but thankfully it's actually not too bad. So I'm going to talk about why it's a little bit more tricky. So, unlike the denominator, which just has multiplication by 2 every time, a pattern you can notice with the numerator is that it's multiply by 2 and then add 1. So there's multiplication and addition in here. So if I have just addition, that's an arithmetic sequence and translates to a linear explicit equation. If it's just multiplication, we have a geometric sequence, which translates to an exponential equation. But when you have addition and multiplication, not as easy, so it's not as clear. But instead of using my recursive pattern to tell me my explicit equation, what I'm going to do is look within the fraction. So like I said, I had a times 2 and a plus 1. That's hard to get an equation from just by itself. So what I'm going to do is I'm going to compare my numerator and my denominator and see if there's a relationship there that I notice. And so I'd like you to think about first, is there a relationship that you notice between the numerator and the denominator in each of those fractions? The relationship that I notice between each of those fractions is that the numerator is 1 less than the denominator. So I do 4 minus 1 and I get 3, 8 minus 1, I get 7, etc. So if I want to do that generally, I can do that every single time. I know what my denominator is, it's 2 to the n, so my numerator is always going to be 1 less than my denominator. 2 to the n minus 1. So here is an explicit equation that will give me any term. So if I wanted to figure out the 156th term, I would plug in 156 for n and plug that into a very powerful calculator because it's going to have a lot of digits and I would get a number. So I would be able to do that without having to go, okay, times 2 plus 1 and times 2, 156 times. Instead, I can just use my explicit equation and jump right to it. So it's very handy. But the point of this is not just to get an equation. That's the first part. The real point is to let n go to infinity. So what that means is we don't want to just look at the partial sum. We want to look at the whole sum. And we only get the whole sum if we go out to infinitely many terms. So I want to look at 2 to the n minus 1 over 2 to the n as n goes to infinity. And if you've ever done limits, this is very similar to limit notation, what I have right here. The only difference is in an actual limit, I would write lim and then say n goes to infinity. So what we're doing here is we are doing limits, but I'm not going to dive into the whole formal aspect of limits that much. You're going to get the concept of it instead. So here, what this means is what happens when n goes to infinity. And can we figure out what happens? Because it doesn't always go to a single number. Now, we have a trick here. I have a 2 to the n in the top and a 2 to the n in the bottom. 2 to the n, if I multiply 2 by itself infinity times, right, if I let n be infinity, that's going out to infinity, right, because it's just doubling. If I double something infinitely many times, I'm going to infinity. So if I just look at this as it is, that's kind of like saying infinity minus 1 over infinity, and it's ambiguous. You could argue that this kind of looks like it's going to 1 for the same reason that all of those look like they're going to 1, but it is ambiguous when you have infinity over infinity. So what we're going to do is we are going to break this up. So this is the same thing as 2 to the n over 2 to the n minus 1 over 2 to the n. And you can see common denominator, I add these up, I get that fraction. So these two things are equivalent. And now I can reduce a little bit. I have 2 to the n over 2 to the n. That's the same thing as 1 minus 1 over 2 to the n. Now, all I have is 2 to the n in this one spot, which is much better for looking at when n goes to infinity. So if you're doing this process and you end up with an equation where we have n on the top and bottom, probably going to want to try to break it up if you can. So now that I'm here, the question is what's happening here? So I already talked about the fact that 2 to the n is getting really, really big. So if my denominator of my fraction is getting really, really big, the question is what happens to the fraction of the whole, the fraction as a whole. So if I have like 1/2, and I have 1 over 100, and I have 1 over 1,000, what's happening to my fraction? It's certainly not getting closer to 1. It's getting smaller and smaller every time. If I were to write these as a decimal, 1/2 is 0.5, going further out. And I just kind of picked those random numbers at random, the 100 and 1,000, just because they're easy to think about. They're not really powers of 2. But thinking about what happens when the denominator of the fraction gets bigger, my decimal would do something like this. Right? So I'm getting closer and closer to 0 every time my denominator gets bigger. So that means when n goes to infinity and the denominator of this fraction goes to infinity, the fraction itself is going to 0. So when I let n go to infinity, 1 minus 1 over 2 to the n goes to 1 minus 0, which is 1. Woo! And that's great that I just got 1, because that's what I expected to get when I was doing my logic, when I was looking at my sequence of partial sums. But now I've more formally shown that this sum is 1 when we get all the infinitely many terms. So that is our method number 3. Get our nth term equation and look at when n goes to infinity. So now I'm going to erase this. And show you our final method. So our final tool for getting a value for a series is to set it equal to x and solve. So I'm going to tell you what I mean by that, why it works, and when it works, because it doesn't work all the time. Those are our 4 methods. You should definitely write them down if you haven't been taking notes already. Okay, so set it equal to x and solve. Before I actually apply that to our series, I am going to remind you of something that you should have learned at some point, but most people don't remember it. And it is how to convert from a repeating decimal to a fraction. So I'm going to use first the example of 0.3 repeating. So there's my repeating decimal, and we all know, or most of us know, that this decimal is 1/3. So now I'm going to talk about how you would figure that out if you didn't know that. So if I have 0.3 repeating, I can set it equal to x, and then I can do some multiplication. So what I've done here is I said equal to x because I want to know what this is. I want to know what a single number is that represents it. So then I'm going to multiply by 10 on both sides. So when I multiply by 10 on both sides, my decimal point shifts over. Now I want you to take a second and think about, why do you think I chose to multiply by 10? I chose to multiply by 10 because I wanted to get this decimal to show up. So here's what I'm going to do. I'm going to break this up, and this is 3 plus 0.3 repeating equals 10x. And that's what I wanted. I wanted some number plus the thing that I started with. Because what I know about this is that it's equal to x. That means this value and this value are the same, which means that I can replace one with the other without changing anything. So I'm going to replace this 0.3 repeating with something it's equivalent to, which is x. So this is 3 plus x equals 10x. And we're going to solve from here. So I'll subtract x from both sides, and I'm going to get 3 equals 9x. So if I have 3 equals 9x, I can divide both sides by 9. And I'm going to get 1/3 equals x. And we already said we knew that 0.3 repeating is 1/3. And this tells me it for sure. So now I'm going to try again with a different one. So let's try this one. So what's different about this decimal compared to the previous one? A key difference here is that we no longer have a single number that's repeating. We now have 2 digits that are repeating over and over. So thinking about the idea that I want to get some number plus my 0.18 repeating on my left-hand side of the equation, am I going to multiply by 10 if I want to get 0.18 repeating? If I want to get 0.18 repeating, instead of multiplying by 10 this time, I actually want to multiply by 100. So that's going to get me 18. Doesn't really look like an 8. 18.18 repeating. And don't forget to multiply on both sides. And so now we have equals 100x. So again, I can break it up. I'm actually not going to write the step of doing the addition. I'm just going to say this is the same thing as 18 plus x. And then I can just solve like I would an equation. So I'll subtract x from both sides. I get 18 equals 99x. So that means 18 over 99 equals x. I can reduce that. That's 2/11 equals x. So 0.18 repeating is 2/11. So this is the process that we're about to apply to our sum. So I have 1/2 plus 1/4 plus 1/8 plus 1/16 and so on equals x. So like I mentioned before, I want to get some number plus what I have up here. So I'm going to write my 1/2, 1/4, 1/8, so on. So that's what I want on the left-hand side. So I want to figure out what I multiply by to make it so I get some number plus this sum. And so this is generally how I look at it. I just line up my terms. And I say, okay, is there anything I can multiply 1/4 by to get 1/2? I can multiply 1/4 by 2 to get 1/2. If I multiply 1/8 by 2, then that's 2/8, and that gives me my 1/4. If I multiply 1/16 by 2, then that's 2/16, which reduces to 1/8. So if I multiply everything by 2, this whole part of my series becomes the 1/2 plus 1/4 and so on. So I always line it up, and that's how I see what I can multiply by. Because in this case, it was the thing that made this 1. It's not always going to be what makes your leading term 1. It is always going to be what makes this part of the series equal the series you started with. So multiplying 1/2 by 2, I get 1. Over here, I get 2x. Don't forget to not set it equal to x. Actually set it equal to 2x, because you multiply on one side, you got to do it on the other. So if I do that, then this here is the same as the series that I started with, is the same as x. So I'm going to swap them out. So this is 1 plus x equals 2x. Let's scoot it up. So we have 1 plus x equals 2x. If I subtract x from both sides, I get 1 equals x. Bam! So I have again shown that this series, 1/2 plus 1/4 and so on, equals 1. And those are the 4 tools that we have in our toolbox right now from the previous term to show that, to get a value for our series. So now I have a few caveats that I want to share. So we got x equals 1. When I do this process, when I set the very first step, when I set my sum equal to x, what I just did is I made an assumption. I assumed that there is some number that represents this whole sum, that I can evaluate this sum and get a single number. So it can be argued that that's not going to happen, that you don't think we can evaluate an infinite sum and get a single number. And I think it's okay to have either of those perspectives. So to argue that 1/2 plus 1/4 plus 1/8 and so on is equal to 1 based on these things, or that it approaches 1. Either way, the idea is the limit, like we were talking about with our sequence of partial sums, when I go farther and farther out, I'm getting closer and closer to 1. I'm never going to pass 1 either. Mathematicians generally have agreed that we can collect infinitely many terms and get a single value if the series is convergent. And so what that means, when a series is convergent, you can tell from the sequence of partial sums that we're approaching things. So that's actually the first main definition of convergence, is using this step 3. If a series is convergent, you can get the nth term equation, or you can show a series is convergent by getting the nth term and letting n go to infinity. That is not the only way to show a series is convergent, and not being able to get an equation for the nth term does not in itself mean that a series is not convergent. We won't be dealing with many equations where you cannot do step 3 or even step 4. The other thing I want to say about this process, setting it equal to x, this works because we have a very specific type of series. What we have is a geometric series, similar to a geometric equation, but it's a series because it's not a list of numbers. So what happens here is each term is 1/2, or I can multiply by 1/2. It's 1/2 of the previous term. So not the value of the sum, but the value of the terms themselves, I can always find by multiplying by 1/2. And so that constant multiple that's happening here is what makes it a geometric series. So I mentioned this is a convergent series. That means it goes to a value. Now, there are also series that are divergent. And this is where having some logic about what's happening is important. So I'm going to give you another series, and another geometric series, in fact. I'm going to give you two geometric series to show you what can happen when we have a divergent series. So here is a divergent series. Why do you think that this series is divergent? Or in other words, doesn't converge to a single value? This is divergent because if I add up all of these terms, then I'm going to get infinity. I'm never going to hit a cap and not stop going. I'm always going to get a bigger and bigger number every time I add things. So this is divergent. It's not going to converge to a single value. However, it's still a geometric series because I'm doubling from one term to the next. So I have that multiplicative property. So if I don't use my knowledge and logic to think about the fact that this is divergent, I might say, oh, it's geometric. Let's set it equal to x and solve. And we can do that. I'll show you how. So what I want is I want some number plus my original series. So the question is, what do I need to multiply by to go from my 2 to my 1, from my 4 to my 2, etc.? So what I need to multiply by is 1/2. Ooh, computer lagged for a second. So I can do that on both sides. So the only piece I need here is to fill in what that number is. 1 times 1/2 is 1/2. And now we can use the same process. So this is the same thing as my original series, which is the same thing as x. So I'm going to swap them out. So I have 1/2 plus x equals 1/2 x. I'm going to subtract x from both sides. That gives me 1/2 equals negative 1/2 x. So I'm going to multiply by a negative 2 to cancel out the 1/2 and the negative to get x by itself. So if I multiply both sides by negative 2, then I get negative 1 equals x. So I just said this series, which is constantly getting bigger, I'm always adding larger positive numbers, and if I manage to add up all infinitely many of those things, I get negative 1. That doesn't make sense, does it? And there are some arguments where that maybe could be useful. But if we're talking practically speaking, that doesn't make sense. Because making the assumption that was this first line, making that assumption, setting it equal to x, was a bad assumption. I didn't use my logic and say, oh, there is not a single number that can represent this sum. No way. If I had made that logical step that said right away, oh, this is divergent, I can't find a number that represents it, I would not have set it equal to x. But I did. So this basically says, if there were some number that represented this sum, that number would be negative 1. Supposing that I did all my math correctly. I don't see any obvious errors. So that's something that can happen when you try to use these methods on a divergent series. And so I can tell this series is divergent just by looking at the terms. Another way, so that's divergent because the terms go off to infinity. Another way you can have a divergent series is when it oscillates. So another series that we looked at last term is 1 plus negative 1 plus 1 plus negative 1, and so on. So let's start by looking at the sequence of partial sums. So my first term is 1. The sum of the first two terms is 0. Then I add 1 to it. Then I subtract 1, oops, and so on. So my sequence of partial sums alternates or oscillates between 1 and 0 over and over and over. So whenever you have a series that isn't going off to infinity like our last one, it's still trapped, but it's not going to a single value. That's the key thing here, is it's going to more than one value. So it is also divergent because it is not converging to a single value. And when you have divergent series, another way you can tell is because you can show through very legal arithmetic manipulation that the series converges to different values. And I said converge, but I shouldn't have said converge. Sorry, that was bad language for me. But you can show that the series equals different things, which means whenever you find that the same sum equals different things, that is illegal. And that means you are probably working with a divergent series like this one. So we have this divergent but not going off to infinity behavior. So here's some cool things you can do with this one. So first thing I'm going to do is I'm going to use the associative property of addition, which means I can group things however I want. So I'm going to group like this. If I group all of my terms here, I'm going to evaluate the parentheses first, and I'm going to get 0. And if I add up 0 over and over, I can tell you with confidence that that's going to be 0. But I can use the same series and group it differently. I forgot to say ... If I group it like this, then I have my 1 at the front, but all of the parentheses again are going to be 0. So I have 1 and I add 0 to it infinitely many times, I get 1. So I just showed the same series. I showed it equal to 2 different values. And that's not all. We can show it equal to yet another value. By setting it equal to x. So this is again a geometric series. This time I'm multiplying by -1 to get from one term to the next. And here I want a number plus 1 plus -1. So to get that, I need -1 to become +1, so I need to multiply by -1. That gives me -x over here, and my leading one becomes negative. So I just flip all the signs here, and then this term is x. So I'll replace that with x, so I have -1. -1 plus x equals -x. Subtract x from both sides. I get -1 equals -2x. Divide both sides by -2, and I get 1/2 equals x. So I have shown x equals 0, or I've shown the sum equals 0, that it equals 1, and that it equals 1/2. You cannot have 3 different values for the same thing. So that is further evidence that this is a divergent series. So that is the crash course on the work that we've done with series so far, using those 4 methods and what it looks like when you have a divergent series.